अच्छा अब ठीक है ना. Okay. Sir, can the boiling of water be considered as free molecular motion? So today you will come to know that what is free molecular motion when I will be telling you about the momentum transfer. Don't worry, okay? Then you will yourself understand whether it can be considered as a free molecular motion or not, okay? Okay, so good afternoon. Okay, good afternoon. Okay, great. So now let's start. Okay. So first of all, let us discuss what we discussed in the last class yesterday. Okay. So we started with the definition of fluids. Okay. So what is a fluid? Okay. We then understood what is mechanics and what we are going to study in fluid mechanics. So fluid mechanics has few parts. First is the statics. We have kinematics also, and we have the dynamics also. There is a difference between kinematics and kinetics. So what is the difference between kinematics and kinetics? That I will be telling you when we will be discussing about the kinematics portion. Okay. And after that, what we discuss about the body force, we discuss about the surface force. I told you that the forces which are acting on the surface, for example, if it is a friction, so friction is acting on surface, okay? If it is adhesion, if it is cohesion, so these all are the surface forces. As far as the weight is concerned, it is a body force. And somebody was saying me that, sir, regarding buoyancy, so buoyancy is a body force or a surface force? So dear students, the buoyancy or the buoyant force, it acts on the volume of a particular, you can say, particular body or particular structure, okay? For example, in Archimedes principle, when I will be telling you, so the buoyant force is actually equal to the weight of the volume displaced by the body. That is the buoyant force, okay? So it is actually acting on the volume of a particular body. So that is a body force, not a surface force, okay? So, and regarding pressure, pressure is a surface force, pressure is acting on the surface, okay, perpendicular to the surface. So these things we discussed. Good afternoon, okay. And what we discussed yesterday, we discussed about bubbles, we discussed about soap bubbles, we discussed about water, you can say droplets, okay. And somebody was saying, sir, how can it burst? Can you please explain how does it burst? So now let me explain you how does it burst, okay. So for example, if you have a, let me take an example of, you can say a droplet. Let us say we have a water droplet, okay. Why is it spherical? It also has a reason. So why are you not drawing a bubble or a you can say water droplet like this? Why you always drawing spherical? There is a reason for that. I'll be telling you that also. Okay. So how does it collapse? So for example, some pressure is acting inside the bubble or a droplet. Okay. And outside we have on the surface we have the surface tension. We have the surface tension on the surface, okay. If surface tension is very high, it will collapse like this. It will collapse, it will not become spherical, it will flow. It will collapse like this. If the internal pressure is very high, it will burst. If the surface tension is very high, it will collapse. It cannot become sphere. It cannot be spherical, okay. So that is what is happening. Or you can say the diameter of the sphere will become very small if the surface tension is very high. That can also happen, okay. So, and somebody was saying that what happens that if we in water, if we mix some syrup, right, corn syrup, and why it happens that the durability increases, okay. So yesterday I also told you that when you dissolve some corn syrup or you can say some glycerin, anything you dissolve which decreases the surface tension. So for example, if you are dissolving some corn syrup, it decreases the surface tension. Now if surface tension is decreasing, now for example, this is, you can say, this is my soap bubble. So surface tension is trying to make it like this. It is trying to decrease the diameter of it, okay. It is trying to become more stable by decreasing the diameter, and the internal pressure wants to expand the diameter. So if the surface tension is small, what will happen? The diameter of the bubble will be high, and it can retain its shape for a longer period of time. That is why the durability also increases, okay. So these were a few questions. Okay. Sir, I don't get how the bulging points comes under a non-wetting fluid. Okay, how does it come? Today we will be discussing about the capillary action. There I will be telling you how the bulging point actually comes. How does it come? Okay, how the bulging point comes. So today we will be discussing about that also. Okay. So we discussed all these things yesterday. We also discussed about the jet case. Okay, so what is the surface tension? What is the you can say excess pressure in case of jet? We also discussed that. Okay. So now today what we are going to do is that first of all we will be discussing some concepts regarding the capillarity, okay, some concepts regarding capillarity. After capillarity we will be going to the viscosity, and after viscosity we will be solving all the questions, previous year gate questions, as well as you can say what questions I think that these types of questions can be asked in examination, so we will be solving some questions also, okay. So now let us start today's topic with the another property of fluids, that is the capillarity, okay. So now let us start with the capillarity. So let me rub this. Duster is, where is duster? Okay. And yesterday I also told you about the angle of contact also, okay. So I have told you that if it is a wetting fluid, then the angle of contact is an acute angle, okay. And if it is a non-wetting fluid, the angle of contact is obtuse angle. And somebody was asking me, sir, can the angle of contact be 0 degree or 90 degrees? So if it is pure water, and you have a pure glass surface, then the angle of contact can be, you can say, 0 degree. Now angle of contact, theoretically you can say, practically also it cannot be 90 degree, but still we have some material. For example, if you have pure water and pure silver, what I did say, we have pure water, and yesterday I told you that there is a substance vinyl, okay. So the name is vinyl hypochlorite. It has 2% of H2SO4. If it is you can say in the boundary condition of, you can say, pure glass, then also the angle of contact is 90 degree, okay. But normally we do not have any material which has, you can say, an angle of contact of 90 degree, but ideally we can have, okay. So what is the did I tell you? So I told you that if you have pure silver, and plus pure water, you can have angle of contact as 90 degree, because the surface is almost flat. The surface is almost flat, okay. But practically we cannot have, because pure silver is also theoretical thing, because you cannot have pure silver, you have to add some adulterants in it to make it stable. You cannot also have pure water, you have to have some minerals have to be there in the water, okay. So that is why all these are theoretical things, okay, not practical things, but obviously we can have. Okay, now let us start with, so I'll be seeing all the questions, don't worry, but let me first of all, you can say, finish what I want to finish today, okay, but because otherwise we'll lag a lot, okay. So today we are going to start with the capillarity, okay. So today another property we will be discussing about the capillarity. We'll be discussing about capillarity, okay. Now capillarity, if somebody asks you that what is capillarity, what you will say that it is rise or fall in a thin glass tube is known as capillarity, okay. Now let us see some physical significances of capillarity, where in practical life we see the capillary action, and why does it actually happen, and where in practical life we see the capillarity action, okay. So let me give you examples of, so when you were small, if somebody of you might be from a village background area, so in village we have lanterns, right. But nowadays every village has electricity, but in earlier days in 1990, late 1990s and earlier 2000, okay. So the village areas used to have lanterns, and they used to have, you can say, wicks, okay. So what is the action in that particular lantern? So what is happening is that, for example, this is a container, it has some oil, it can be a kerosene or any oil, but generally kerosene, okay. Now this is a cotton wick, if you drop this cotton wick in this oil, due to the forces of adhesion and cohesion, it moves up to this surface, and you light it with a matchstick or something, okay, and then you have fire, okay. So that is the physical significance where we have seen the capillary action. Similarly, for example, if you are growing crops in a particular field, the roots of the plant, they absorb water. For a process that is known as photosynthesis. How does that happen? So that also happens due to the capillary action of soil. So what happens is that, for example, this is, you can say, ground surface, and here we have some water level. Due to capillary action, this water level from the water table, it moves up to this zone known as the root zone, and these are the crops So what happens is that they absorb water and make their food, which is known as the procedure known as the photosynthesis, with the help of sunlight. Okay, so that is the physical significance of capillary action. That is what is happening in nature also. Okay, so now what is actually happening is that, now what is the reason of capillarity? The reason of capillarity is the forces of adhesion and cohesion. Forces of adhesion and cohesion. Forces of adhesion and cohesion. What is an adhesion? What is a cohesion? We have already discussed in the last class, but still let me again repeat it. Adhesion, add. So you add to different quantities, 2 plus 2, 2 plus 3, 2, you add to different number. So add means to different. Similarly, adhesion means the force of attraction between two different, you can say, particles, or between two different media is known as adhesion. Clear? And cohesion, co means same. Co means same, right? So cohesion means the force of attraction between same particles is known as cohesion. Clear? So that is adhesion and that is cohesion. For example, adhesive. Fevicol is an adhesive. If you apply Fevicol over a surface and you stick, you can either stick, you can say a paper or anything you can stick. So adhesion means between two different surfaces. Clear? And cohesion means between same surfaces. Clear? So that we have already discussed regarding the forces of adhesion and cohesion. Okay. We also, yesterday in the last class, we also discussed about the angle of contact also. And somebody was asking, I just remember, somebody was asking in the last class, sir, can you give us example of a non-wetting and wetting fluid? I told him that, for example, if you have water and if you have glass, it is generally considered to be a wetting fluid. If you have mercury, if you have glass, it is generally considered to be as a non-wetting fluid. But water, I cannot say that water is a wetting fluid, not wetting fluid, because water can behave differently in different medium. For example, if you put water in glass, right? So it will be a wetting fluid. It will be a concave surface. Okay. But if you put water, let's say you have a leaf of a plant, and if you put water on the leaf of the plant, so what happens is that you can see that spherical droplets. It is trying to have the minimum surface area. Clear? So water also can behave differently depending on the medium on which you are placing it. So we cannot say that water is a, you can say, a wetting fluid or non-wetting fluid. If you are mentioning any fluid as a wetting or non-wetting fluid, you should also mention the confinement or the container in which you are putting that particular fluid, whether it is glass or which type of container is that. Okay, then only you can define a particular fluid as a, you can say, wetting fluid or a non-wetting fluid. Okay, now let's come to this topic, capillarity. So what happens is that, now let me rub this. Okay. And somebody was saying, sir, what is the exact definition of cohesion and adhesion? So dear students, so don't go into the, you can say, mugging up things, that what is adhesion, I have to learn what is adhesion. If somebody even in interview asks you what is adhesion, you should have the concept that you can explain what is adhesion. Just like I was explaining you that, for example, this is a duster and this is a surface. So for example, whatever you have in the vicinity, for example, you are sitting on a chair and somebody is asking you regarding adhesion, cohesion, whatever you have in the vicinity, you make use of that and explain him that this is adhesion, this is cohesion. You can use anything. Okay, you can also use palms also, the difference between the force of attraction between two different surfaces, adhesion, and for the same, you can say, media, it is cohesion. You can also explain like this. Clear? So now capillarity, I was explaining about capillarity. For example, we have a container. Let us say we have a container, a big, you can say a beaker is there. Clear? And it has some water. For the time being, let us only consider water. Clear? Now let me put a thin glass tube inside it. You can also perform this experiment. Let me put a thin glass tube inside it, like this. A thin glass tube has been put inside it. Now what will happen? Because this is water, this is glass, and we know that if water is in a glass container, it behaves as a wetting fluid. So what will happen is that it tries to cover maximum area of the glass. It will try to cover the maximum area of the. So what will happen is that this water will go up to this level. Obviously it will go to this, but after that what will happen is that it tries to cover the maximum area of the glass, and due to the force of adhesion and the cohesion between the particles, slowly it moves upward. It goes here. This height is, let us say it is h. Clear? And this is known as the capillary rise. capillary rise. Clear? Why? Because water is a wetting fluid, it tries to cover maximum area of the glass. Now depending on the weight of the fluid, it has to be balanced by the surface tension. We will be coming to that also, but this height actually depends upon the weight of the fluid acting downwards and the surface of tension acting upwards. Coming to that, don't worry. Clear? Now let me take another case. So this is water, this is glass. Let me take another case. Let me take, again, let us say we have a glass beaker, but in the glass beaker we have mercury, Hg. We have mercury. And again you put some glass tube inside it. Now this is mercury. So we know that mercury, if it is an inside glass, it behaves as a non-wetting fluid. Non-wetting means that it will try to cover minimum area. It will not try to get more involved with the, you can say, this glass tube. It will not try to get more involved with this glass tube. So now what will happen is that obviously it will go up to this level, but after that what will happen is that it will slowly come downwards and have this position like this. So you can see that there is some difference. Let us say that again it is H. This is known as the capillary fall. Capillary fall or capillary depression also. Capillary fall or depression. Capillary fall or depression. So this capillary rise and capillary fall due to the forces of adhesion and cohesion is termed as the capillarity. You can also perform this experiment at home. Clear? Now how to measure this H? How much is this H? So I told you that the weight of the fluid which is above this, you can say, layer, it will be counteracted by the surface tension. Clear? Now for example, this is this tube. I have put this tube here. So this was the water level here, and this is the capillary, you can say, height, and this is a concave surface. So this surface is known as the concave surface, concave, and this is known as the convex. Sometimes in question it is mentioned that it has a concave meniscus or a convex meniscus. So this shape is known as the meniscus, the upper shear meniscus. Upper portion is the meniscus. Okay. So this is a concave meniscus. Concave meniscus, and this is known as the convex meniscus. Convex meniscus. Okay. Now somebody was trying to ask me, sir, why this shape is actually happening. Okay. Now this I will be explaining you here. Why this shape is happening. Why this concave, why this convex. Okay. Now let us see the topmost surface. So when I explained you regarding the surface tension, I told you that, for example, I gave you this example. Let us say this is a beaker. We have one fluid particle here. It is being pulled from all the directions. So the resultant force is 0. And this particle which is at the surface or at the interface of air and water, so this particle has some forces like this, and it has some tangential forces also. Cohesion forces also, because here also we have one particle, here also we have one particle. So it has a resultant inward force, as well as it has the tangential force on the surface, a tensile force on the surface. It has a tensile force on the surface. Now just try to imagine what is happening. So for example, you have a beaker. On the beaker, the surface, the topmost surface has tensile forces. And it also has inward forces. So this has inward forces also, resultant forces, and it also has the surface tensile forces. Now you think what will try to happen? So what will happen is that on the surface there will be a thin membrane type will be formed. Okay, a membrane type of structure will be formed. Okay, so that is why you can see that the insects which are even denser than water, they can, you can say, run on the water surface due to the surface tension, because a thin membrane is formed. Now what is happening at this interface? So what is happening at this interface is that you have this water molecule. This water molecule with the force of cohesion is being pulled by the neighboring water molecules. But it also has a, you can say, adhesive force with the wall of the beaker. So here, when this meniscus is formed, because a membrane will be formed, so we will have a resultant tensile force per unit length. And that resultant tensile force per unit length is known as sigma, or the surface tension. So this is also a question. That's when you were explaining us this, you told us that the net force is in the inward direction, downward direction. But now when I will be deriving the formula for the capillary rise or capillary fall, I will be saying that sigma is acting in this direction. Sigma is acting in this direction. Why? So that is the reason. I have not seen your questions. I will be seeing your questions. Don't worry. Okay. So first of all, let me finish this topic. Then I will come to your questions also. Clear? Now, what about the contact angle? So this is the contact angle theta. How to calculate contact angle? Yesterday we discussed. But still, if you want to again ask me, what is, sir, how to calculate the contact angle? Now let me rub this. Now how to calculate the contact angle is that, for example, this is this tube. This is a very thin tube, but still I have made a very thick tube. Okay. This is some, you can say, capillary, a meniscus is formed. Let us say it is a wetting fluid, a meniscus is formed. Okay. So what you do is that this is a curve, it has some curvature, and we know that from the concept of mathematics that if you draw a perpendicular line to this curve and this curve, it will meet at some point, and that will be the radius of this curve. Now you do one thing, from this radius of this curve, so the point where it is meeting, drop a perpendicular where it is meeting. Okay, and to this perpendicular make a tangent in the direction of the meniscus. So you make a tangent in the direction of the meniscus like this. You make a tangent in the direction of the meniscus. Okay, and the angle between this tangent and the wall surface is known as the contact angle. Similarly, if you have mercury, what you do is that again make a perpendicular, it will be meeting at this point. This will be the radius of this curvature. Clear? Now the point where this meniscus is meeting this glass point, just make a perpendicular here like this, perpendicular, and from this point make a tangent in the direction of the meniscus, and the angle between this curvature and this is the contact angle theta c, or theta whatever you want to call it, theta c, contact angle. That is how we measure the contact angle. Okay, so that is how we measure the contact angle. Clear? So now I was at this. So how to calculate this capillary rise? Clear? Now let me rub this. Clear? Now let me rub this. Okay, now, and this is the same reason, yesterday somebody was asking me, sir, why don't we calculate the surface tension with the area? Why we calculate just with the length? I told him that if you want to calculate with the area, then surface energy is the term. If you are calculating just with the length, then surface tension is the term. If you are calculating just with the area, then surface energy is the term. And I also told you that surface tension is equals to surface energy divided by area. This also we discussed yesterday. Clear? Now let us see this. Okay. Now this fluid which has risen up to this height h has some weight acting downwards. Yes, clear. So it has some weight acting downwards. Clear? And this weight will be counteracted. This is sigma in this direction. So in this direction it will be sigma cos theta. It will be sigma cos theta. So how much will be the weight? So the weight will be equal to gamma into, you can say, gamma into volume will be equal to the weight, and it should be equal to sigma cos theta. Clear? Okay. So How much will be this volume? So this is a cylindrical, you can say a cylindrical tube is there. So how much will be the volume? Gamma into, because we know that gamma is equals to weight per unit volume. From there we have got this. So gamma into pi by 4 into d square into this height h, that will be the weight of this fluid in the tube, and that should be equal to sigma cos theta. Sigma cos theta. Clear? Sigma cos theta, but this sigma cos theta is with, you can say this sigma cos theta, the unit is force per unit length. This is sigma cos theta. Sigma is equals to force per unit length. Okay. But if I want to determine this force, because weight is a force, so what I have to do? I have to multiply it with the length also. So on which length this surface tension is acting? So you can see that this surface tension is acting at the circumference of the circle. For example, if it is a tube, so surface tension is acting at the circumference of the circle. Clear? So circumference would be equal to pi into d. Into pi into d. Okay, now let us see what can I get. So h will be equal to, so dd get cancelled out, so pi and pi here. So it will be equal to 4 sigma cos theta upon, so 4 sigma cos theta divided by gamma into d. And gamma, we also know that from the properties, we also know the weight density is equals to rho into g. That is the weight density. Clear? So I can also say that, or 4 sigma cos theta divided by rho into g into d. Rho into g into d. Where theta is the contact angle. Theta is the contact angle. Clear? The same formula is also valid for the non-wetting fluids also, and theta for this interface, you should remember two thetas. First is the theta between pure water and pure glass, that is 0, and the theta between mercury and glass. The theta between mercury and glass is generally taken as 128 degrees. 128 degrees between mercury and glass. So we'll be getting some negative value. Negative means it is depression or fall. Clear? And here, if pure water and glass is used, if pure water and glass is used, then theta is equals to 0 degree. And if theta is equals to 0 degree, cos 0 will become equal to 1. So h will become equal to 4 sigma divided by rho into g into d. Divided by rho into g into d. Clear? Okay. Now let me see some questions. Yeah, in some books it is also given as 130 degrees. In some books it is also given as 130 degrees. Okay, but I have seen 3 or 4 books. One is DS Kumar, another one was White. So in those books it is given 128 degrees. Generally it is mentioned here in question, but not mentioned. Either you can take 130 or you can take 128 degree. You will be getting a difference of hardly 0.1 or 0.2 difference. You will be getting. Okay, don't worry. Yes, the surface tension, the component of the surface tension, or the vertical component of the surface tension is acting against the weight of the fluid. Okay, sir, what about sigma on the left wall of the capillarity? Left wall of the capillarity? Which one? This one. Here also we will have sigma. Here also we will have sigma. We have sigma on the whole circumference. We have, for example, let me draw a top view. If I draw a top view, so this is the, you can say this is the top view of this glass. So we have sigma everywhere. So here also we have sigma. Here also we have sigma. Sigma per unit length is everywhere. So if you want to calculate the resultant force, so resultant force will be equal to sigma into pi into d. That is the resultant force. So sigma is acting on the circumference. Sir, if you put capillarity Okay, please repeat. I will repeat it again, don't worry. I will repeat it again, don't worry. I will repeat it again, don't worry. Let me use another marker to make you explain it once again. Okay, sir, please repeat, please repeat. Okay, sure, sure. Yeah, that is the same reason. So this is Ranga, some name is there. Okay, so sir, yesterday while explaining surface tension, you drew the resultant force acting on the particle at the surface and now downward direction. Okay, so that is the what I have explained. So yesterday what I explained you is that the resultant force is acting downwards, and today I told you that there is a tangential force. Okay, so what is happening is that a particular surface, a particular liquid, due to surface tension, it wants to have minimum surface area. A particular surface, a particular liquid, due to the you can say due to the stability, it wants to have minimum surface area, because if you have the minimum surface area, you will have the minimum surface energy. Clear? So some, for example, this is a, you can say, particle like this. Okay, so this is acting downwards, the resultant force is acting downwards, but on the surface also, yesterday I also explained you that on the surface also, these are pulling each other. Due to the cohesion, these molecules are pulling each other due to cohesion. And at the interface, we have a resultant force. So here we have a resultant force downwards, and at the interface, we have a resultant force in this direction. We have a resultant force. So that is a surface tension per unit length. If you are calculating it with the area, it will be surface energy. If you are calculating it with the length, with the circumference, it will be surface tension. Okay. So let me again repeat it, because a lot of people are saying that, sir, repeat it again. Okay. So let me again repeat it. Okay. So now let us repeat it with the capillarity. So what is capillarity? If somebody asks you what is capillarity, you will say that the rise or fall in a thin glass tube, okay, due to the forces of adhesion and cohesion is known as capillarity action or capillarity. Okay. So now what does it mean? So it means that, so can I rub this? First of all, note it down. Can I rub this? I will again explain. Can I rub this? Okay. Okay, कुछ समझ नहीं आ रहा. Okay, don't worry. Let me again explain. Don't worry. Okay. First of all, note it down. Let me rub it, and let me again explain you. Don't worry. Let me again explain you. Okay. Now I am rubbing this, and I am again explaining you. Okay. I am again explaining you. For example, you have a beaker. Now this is a big beaker which I have taken, and this beaker has some water up to this level. It has some water. Clear? Now what have I done? What have I done is that I am taking a very thin glass tube, and I am putting a thin glass tube inside this beaker. Let me draw this glass tube with the help of another marker. Let us say this is a glass tube. Inside this beaker, this is a glass tube. Clear? We know that if water is present in a glass container, it will behave as a wetting fluid. Now what is wetting fluid? Wetting fluid is that fluid which tries to have the maximum area of contact, with the surface, with the glass surface. It tries to have the maximum area of contact with the glass surface. Clear? Now what is happening is that if you put this glass tube inside water, first what will happen is that the water will come up to this point. the water will come up to this point. That is natural. Okay, so water will come up to this point. But this is the property of water to have maximum area, to cover the maximum area. Now what will happen is that these water molecules, because it is a very thin tube, so water molecules are very close to, the water molecules are very much close to the surface. So which force will be predominant? So the adhesion force will be predominant here in the glass tube, because it is very thin. Okay, so adhesion forces will be very predominant. So what will happen is that the molecules will try to stick to the glass surface. The molecule will try to stick to the glass surface and will try to cover maximum area. And here you can see that we have some height h. So what appears is that the glass has reached up, the glass has come up to some height. So that is known as the capillary rise. So it is very small. In the last diagram I drew it like this, but it is very small actually. It is very small. Clear? So if I draw it properly, this due to this force of adhesion, if I draw it properly, so it will be like this. It will be like this. So the water level will come up to this point. Although it is very small, but I have drawn a very big. Okay, although it is very small, hardly few millimeters, depending on the size of this, depending on the size of the tube. If the size of the tube is very small, it will be very high due to the force of adhesion, very high. Clear? Okay, so it will try to cover the maximum area of the glass due to the you can say excess adhesive forces. It will try to cover the maximum area of the glass, and it will appear that it has traveled some height h. Okay, now this is water up to height h. Clear? This water, this much of water has some weight acting downwards. Just imagine it like this. For example, I have two hooks. There are two walls. One wall is this, one wall is this. I have two hooks, and I have hold those two hooks, and I have, you can say, suspended myself in the mid-air. So those two hooks, so I will be facing some forces on that on my two hands. So that is the surface tension. And when I am suspending in mid-air, so my weight is acting downwards. So that is the weight of this fluid acting downwards. So you can also imagine it like this. So you are holding some two hooks, right, on, you can say, on two rigid walls, and you are suspending in mid-air. So your weight is acting downwards. So let me again draw this. So these are the two walls. So these are the two hooks here. So I have hold these two hooks, and I am suspending downward like this. So this force here is the surface tension. In case of fluids. In case of this, it will be reaction force, but in case of fluid, that is surface tension. And my weight is also acting downwards, weight. So here also, the weight of this fluid will be acting downwards, W. Simple. Clear? Now, how much will be the weight of this fluid? So we know that the weight density is equals to weight per unit volume. It means that if I multiply this gamma with volume, can I get the weight? Yes, weight will be equal to gamma into volume, the volume of this fluid. So how much is the volume of this fluid? So we can see it is a cylindrical glass tube. It is a cylindrical glass tube. If it would not have been cylindrical, if it would have been triangular, we would have got some other values. Clear? But this is a cylindrical glass tube. If it would have been some conical, we would have got some other values. Clear? But it is a cylindrical glass tube. So what we will get? So we will be getting W is equals to gamma, and the volume of a cylinder is pi d square by 4, area of the bottom, and multiply this height h. This is the weight. Now this is the weight acting downwards. So we have some forces acting upward also. So for example, if sigma is acting in this direction, this is theta. So this will be sigma cos theta. This will be sigma sin theta. So this weight is acting downwards, and sigma cos theta is acting upwards. So this is the sigma cos theta force which is trying to balance this weight. Clear? So this weight should be equal to sigma cos theta multiplied by, because sigma is what? Sigma is force per unit length, surface tension. Sigma is surface tension. Let me write it here. Sigma is surface tension whose unit is force per unit length. Force per unit length. Clear? So, because weight is a force, I cannot equate force with a force per unit length quantity. I have to multiply it with length to get the force. I have to multiply sigma with some length quantity to get force. Clear? So, sigma cos theta multiplied by some length quantity. So, what is that length quantity? So, we know that this sigma, let me again draw this. This is the front view and this is the top view. This is the top view. So, sigma acting per unit length, sigma. Clear? So, this sigma is acting on the circumference. Sigma is acting on the circumference of this glass tube. So, if I multiply sigma cos theta with the circumference, that is pi into d, can I get the total force? Yes, I can get the total force. So, that is the total force. And what is W? W is actually equal to gamma into pi by 4 d square into height h. So, if you solve it, so d get cancelled out, clear? Pi get cancelled out, okay? So, our height, it will be equal to 4 sigma cos theta upon gamma into d, and gamma is equal to rho into g, that we already know. So, h will be equal to 4 sigma cos theta divided by rho into g into d. Rho into g into d. So, that is the formula for capillary rise, and the same formula is for the capillary fall also. So, this is important, right? Because questions have been asked directly from this formula, because I will be solving some questions after this topic, after the viscosity actually, okay? So, this is a very important formula, clear? So, very important, the capillary rise or capillary fall formula. And theta for water and pure water and glass surface is considered to be 0 degrees. And theta for mercury and glass surface, it is nearly 128 degrees, and in some books 130 degrees also given. So 128, 130, whatever you want to take, but generally it will be given to you in question. Clear? So that is the formula for capillary rise or capillary fall. Now there is one more concept which is nowadays asked generally. The another concept is annular capillarity. It is a very famous concept. Just after 2014 or 15, questions have been asked from this topic. That is the annular capillarity. So now let's go to the annular capillarity. First of all, note it down. Okay, then we'll move to the annular capillarity. Is it clear now? Is it clear now? Is it clear now? Yes, tensile forces act on the surface of the particles. Yes, correct. Okay, so how the tensile forces are acting? Let me again explain you how the tensile forces are acting. Let me change the marker. Yeah, so how the tensile forces are acting? So you can, let me again draw a big, you can say big tube. So this is a big tube. This is a big tube like this. So at the surface, let me take this molecule, this water molecule at the surface, this water molecule. So this water molecule tries to come close with this water molecule, and this tries to come too close to this water molecule due to the force of cohesion. So here also we have water molecules, here also we have water molecules. So you can see that between two water molecules, they are getting stretched. Okay, so for example, if somebody is pulling you, I am also pulling you, so your hand will get stretched. And what is stretching? So stretching means tensile. Okay, so for example, this is a duster. I am also trying to pull this duster. We have some other person, he is also trying to pull this duster. What will happen to this duster? It will be pulled. So that is a tensile forces acting, and the resultant tensile forces will be acting somewhere here, sigma and sigma per unit length. Clear? Okay, shall we proceed to the annular capillarity? Okay, great. Now let's move to a new topic, that is the annular capillarity. This is a new topic, annular capillarity. Let me rub this. Okay, now Annular capillarity. Just check the spelling. A-double-N, yeah, correct spelling. Annular capillarity. Now, what is annular capillarity? So, questions have been asked from this topic. The questions are like this. For example, if you have a beaker, clear? In this beaker, you have some water. You put some glass tube inside it, a thin glass tube inside it. Clear? And inside this tube also, you are putting some, you can say, a solid tube. You are putting some solid tube, and this is solid. This is not a, you can say, glass tube. This is not a hollow tube. It is a solid tube. Okay, the diameter of this is, let us say, it is D1, and the diameter of this rigid is D2. Rigid tube is D2. So D1 is the diameter of the actual tube, and D2 is the diameter of that rigid tube or the solid tube which you are inserting inside this tube. And questions are being asked, what will be the capillary rise or capillary fall? For example, it is water. Let us say it is water, so obviously there will be capillary rise. So capillary rise will be there like this. This and this. Let me zoom it. Here. Let me zoom it. So this is the rigid tube inside it. So we have the capillary rise in this tube also and this tube also. We have the capillary rise in both the tubes. We have capillary rise. So okay. So let us say that this is the capillary rise H up to this portion. Let us say here we have water and this is our H. This is our H. Okay. Now nowadays questions are being asked regarding the annular capillarity, and this has a diameter of D1. This outer has a diameter of D1, and this small has a diameter of small D2. D1 and D2. D1 up to this portion. Now what we can do? Do the same thing which I have just told you. Do the same thing. What you do is that you equate the weight of the fluid. With the upward tensile forces. Okay, so obviously here we have some sigma. Here also we have the same sigma. Because if it is of uniform composition throughout the periphery, we will have the same sigma everywhere. Here also same sigma here. So if this is theta, this will be cos theta. Can we do the same thing? Yes, a lot of you would have already done the same thing. Now let us do the same thing. Now let us compare the weight with the sigma cos theta multiplied by the length. Let us equate this. So what will be the weight of this fluid? So if you look it from the top view, so this is like this. So this is solid. And here we have water. Here we have water like this. If you look it from the top view, you have like this. So how much will be the weight? So weight is actually equal to gamma into volume. Now how much will be the volume of this fluid? So the volume of this fluid will be equal to gamma into pi by 4 into d1 square minus pi by 4 into d2 square. Can you see? The pi by 4, the outer minus inner, I will get the total volume into h, into the height h. Because height will be equal. Height will be equal for this also we have the equal height, this also we have equal height will be equal. So pi by 4 d1 square minus pi by 4 d2 square into h. Can I simplify it a little bit? Yes, I can simplify. So it will be equal to gamma into pi by 4 into d1 square minus d2 square into h. This is the weight. Clear? Equation number 1. Let us say it is equation number 1. We have to equate this weight with the upward force. So what is the upward force? Sigma cos theta and multiplied by the circumference. Multiplied by the circumference. So can I say that for this outer tube, so this, let us say that this is sigma cos theta into L. So I will say that this sigma cos theta into sigma cos, outer one is pi into d1, outer one is pi into d1, and plus here also we have the surface tension, here also we have surface tension, pi into d2. So pi into d1 this one, and pi into d2 this two, plus pi into d2. This is equation number 2. Equation number 2. Now can I equate these two equations? Can I equate these two equations? Yes, I can equate these two equations. Now what will I get? Now let me equate it. So I will be getting gamma into pi by 4 into d1 square minus d2 square into h is equals to sigma cos theta into pi d1 plus pi d2. Pi d1 plus pi d2. What I need to get? I need to get the value of this h. I need to get the value of this h. Can I get the value of this h? Yes, I can get. What is a square minus b square? A minus b into a plus b. Okay, so that is how we can solve it. So let me solve this here. Let me solve this here. Let me solve this here. Now let's see what can I get. First of all, note it down, then I will be solving it here. Okay, now, so it will be equal to gamma into pi by 4 into d1 square minus d2 square. I can write it as d1 minus d2 into d1 plus d2. So d1 minus d2 into d1 plus d2 and into h is equals to this value. So sigma cos theta, can I take pi common? Yes, I can take pi. So d1 plus d2. Clear? Can I cancel d1 plus d2? Yes, I can cancel. So d1 plus d2 and d1 plus d2 get cancelled out. So what I will be left with? So I will be left with h will be equal to, so h will be equal to 4 will go there, 4 sigma cos theta, pi will also get cancelled out. So pi and pi also get cancelled out. So 4 sigma cos theta divided by gamma into d1 minus d2 into d1 minus d2. That is the formula for annular capillarity. And gamma is equals to rho into g. Gamma is equals to rho into g. That is the formula for annular capillarity. Okay. So there are some formulae in fluid mechanics which I feel that they have to be derived. But there are some formulae in fluid mechanics which I don't think that they have to be derived. For example, when in the boundary layer flow, we will go to the Blasius solutions. So Blasius solution is regarding the thickness of the boundary layer for turbulent flow. So those equations have not to be derived. Those equations have to be, you can say, learned. Not just equations, the formula have to be learned. The Blasius solutions. But regarding the parallel plates, regarding the, you can say, concentric plates and concentric pipes also, those equations have to be derived. Clear? So what I feel that what has to be derived, I will derive it. But what I feel is that there is no need to derive all these things. Those are the standard results that have to be learned. Okay, that have to be learned. So H is equals to 4 sigma cos divided by gamma into d1 minus d2. Now how the questions are coming? The questions are coming like this. So we have a glass tube will be given to you, and it is told you that inside the glass tube we have a rigid glass tube of diameter this much. So how much should be the rise or how much should be the fall in the tube? and that is calculated with the help of this formula. Same goes with the fall also. It is regarding rise, same goes with the fall also. So now what is happening? Now what is happening? Is it decreasing or is it increasing? What do you think? The height, is it decreasing compared to this value? Compared to this value, 4 sigma cos theta. So earlier we had 4 sigma cos theta divided by rho into g into d. And now we have 4 sigma cos theta divided by gamma is rho g into d1 minus d2. Is it increasing or is it decreasing? Is it increasing or is it decreasing? Sir, for okay, increasing, yes, correct. So somebody asked me a question, sir, for weight we are subtracting the diameter, while for, okay, so somebody is saying that, sir, for the surface tension you are subtracting the, sorry, you are adding the diameter, but for the, you can say for the weight you are subtracting the diameter. Why is it happening? Okay, now let me again tell you. Okay, yes, increasing, correct. So we can say that as, because the distance is decreasing. So as the tube gets thinner and thinner and thinner, so I can say that there will be more capillary rise or more capillary fall. So that we can say that is an interview question. So as the diameter gets thinner, or if there is some angular capillarity, it either decreases or it either increases. Okay. Now somebody is asking me, sir, in the surface tension, you the question was you added the diameter, but in the weight you subtracted the diameter. Why? Now let me again explain it, don't worry. Okay, have you noted down? Shall I rub this? Okay. Okay. Now somebody is asking me that's why in the weight you decrease the diameter and in the case of the surface tension you increase the diameter. Let me tell you that surface tension is directly proportional to the number of surfaces or the surface area. If the surface area or the number of surfaces are increasing, the surface tension will increase. But if you are decreasing the quantity of the matter, the weight will decrease. Simple. For example, this was a glass tube, this is a tumbler, a container, this is a glass tube. Okay, let me draw this glass tube up very, you can say, with big diameter. This is a glass tube like this. Clear? And here inside it we have a rigid, or you can say a solid tube. If I look at the front, if I look at the top view, if I look at it from the top, it will be like this. This is the outer one. This is, let us say, D1. This is, let us say, D1. And inside we have this rigid D2, rigid or solid tube. So why do we have weight? We have weight due to the quantity of matter. So you can see that if I am occupying that space, my weight, my quantity of matter is decreasing for a particular volume. For example, this is a duster. This is a container. This container has, let us say, 1 liter of water. If I place this duster inside it, so how much will be the water? Will it increase or will it decrease? Obviously the water will decrease, because the duster will also try to occupy its volume. If it will try to occupy its volume, it will decrease the matter of water. That is the case why I have decreased the water. But as far as this is concerned, surface tension is concerned, surface tension is directly proportional to the number of surface areas or number of surfaces you have. So we have one surface here and we have one surface here. So we have sigma here also and sigma here also. So we have sigma, this is the capillarity, We have sigma here also and we have sigma here also. So that is why it is increasing. That is why it is increasing. Clear? Okay. That is regarding the annular capillarity. Now let's proceed to a new property of fluid, that is the viscosity. Let's proceed to viscosity. Clear? So are you getting it till now? Whatever I have told you, are you getting it? We have not solved numericals, obviously we will be solving after the viscosity, we will be solving numericals. But till now, whatever I have told you, are you getting it? Are you getting it? Sir, how will be the derivation of for capillarity? Capillarity is a property, you can say. Capillary rise and capillary fall, we can do the derivation. For how to do the derivation capillarity, obviously we can't. That is a property. We cannot do derivation of, you can say, a property. Sir, what's your name? My name is Bahubali. Okay. Okay, so regarding capillary fall, you can do the same thing regarding the capillary fall also. For example, if you have capillary fall, now this is a capillary fall, okay. For example, this is a fluid. So here we have capillary fall. This is the height h. This is the height h of the capillary fall, okay. So this height h is trying to, you can say, trying to lift it up. This obviously, when I will be telling you about the Pascal's law, you will be understanding. So if this is a, you can say, water, this water is trying to lift it up. If this is mercury, this mercury is trying to lift it up, but due to the surface tension, it is trying to go down. Due to surface tension, it is trying to go down, okay. So that is how you can determine it, and I will be telling you what is rho gh. It is actually called rho gh, okay. So don't worry. In the Pascal's law will be Bahubali of fluid mechanics. No, I am not a Bahubali of fluid mechanics. They are very senior professors than me, okay, who are teaching from last 20 years, 25 years, okay. So obviously I am not the Bahubali. I am, you can say, student of those Bahubali people, okay. Okay, now let us move to a next property of fluids, and that is known as the viscosity. Viscosity. Spelling, just check the spelling. Yeah, viscosity. Okay, viscosity, next property, that is the viscosity. And one more thing. So this is also an interview question. The question was like this. So the capillary rise or capillary fall, on which factors does it depend? On which factors does it depend? So now let us discuss that, then we will come to viscosity also. So now, factors affecting capillary rise and fall. So whenever somebody is saying you what are the factors influencing that particular property, just write down the formula and you will see that what are the factors affecting. So we know that H is equals to 4 sigma cos theta divided by rho into G into D. So the first factor which will be which will be affecting the capillary rise or capillary fall will be the density of that particular material. Simple. Acceleration due to gravity is constant, 9.81, until and unless you are not on moon. because on moon the acceleration due to gravity is 1/6 of that of earth. Clear? So diameter of the you can say that glass tube, that also affects the capillarity high rise or fall. The contact angle, it depends upon the medium, whether you have glass tube or whether you have some other tube, it depends upon the medium. This sigma, on what factor does it depend? This sigma. So yesterday somebody was asking me. So this sigma, on what factors does this sigma depend? So sigma depends first of all on temperature. Now, if the temperature is high, what is happening is that the force of attraction between you can say molecules, it becomes very weak. You can say lessens. Okay, it becomes very weak, the force of attraction between molecules. Why? Because the kinetic energy of the molecule increases. If the kinetic energy of the molecule increases, the force of attraction becomes small. Okay. So now what is happening is that if force of attraction between the molecules is small, that will ultimately decrease the surface tension. So I can say that if the temperature increases, the surface tension or sigma decreases. It also depends upon the solvents. Solvents in fluid. For example, if you are mixing something with the fluid which is immiscible, which does not get mixed with that particular fluid, so what is happening is that ultimately the surface, molecular forces between the adjacent molecule, it will further decrease, and sigma will decrease if solvent is immiscible. If you are adding something, for example, you are adding, you can say fructose you are adding to water. If you are adding fructose to water, or if you are adding some grease to water, what will happen? Ultimately, the surface tension will decrease. So it depends upon basically on two factors, that is the temperature and the solvents which you are adding, in particular, you can say fluid. Okay, sir, what is the critical temperature we consider for surface tension? Okay, surface tension generally you can say surface tension depend on the various material, or depends on the various material. For example, regarding the surface tension, I just got one click. So somebody was saying that, sir, specific gravity is equals to density of a particular material divided by the density of a standard fluid. And I told you that in case of fluids, the standard fluid is taken as water at 4 degrees Celsius. Clear? Somebody was saying that, sir, does the mass density of mercury, for example, I told you that for mercury it is 13.6. So is it also for 4 degrees Celsius? My answer is no. Because we are comparing our density with some standard fluid. And standard fluid is taken as water at 4 degrees Celsius. For fluid it is water at 4 degrees Celsius. For gases it is, you can say, dry gas at STP, which is 1.21 kilogram per meter cube. But for fluids, for liquids, it is water at 4 degrees Celsius. You can measure the density of mercury at any temperature you want. But the standard would be water at 4 degrees Celsius. For example, if you want to calculate the specific gravity of benzene. So we know that the benzene is gas. If you decrease the temperature, what will happen? It will slowly convert to the liquid form. So we generally measure the specific gravity of benzene at 20 degrees Celsius. So for different particular substances, we have different temperature. For particular substance, we have different temperature, but the standard has a particular temperature. For standard, that is 4 degrees Celsius. For, you can say, for liquid it is 4 degrees Celsius. For water it is 4 degrees Celsius. Otherwise, you can have this numerator can be at any temperature. Clear? Okay, how to draw angle of contact for conical surfaces. Okay, we'll be coming to conical surface when I'll be solving about, you can say, when I'll be solving about some numericals, then I'll be telling you how to draw it for the conical surfaces, how to draw the angle of contact for the conical surfaces. Don't worry. Clear? Now let's proceed to our this property, that is the viscosity. Now let's proceed to this property, that is viscosity. So these are the various factors which influence the capillary rise or fall or capillarity. Now let's move to viscosity. Now very interesting topic and very important as far as the gate point of view is concerned, very important also, the viscosity. If somebody asks you what is viscosity, what you will say? The resistance to flow. The resistance to flow is termed as viscosity. The resistance to flow is termed as viscosity. Clear? But how that resistance is coming? Now let us understand that how that resistance is actually coming. Okay. Now let me take a solid surface. Now let me take a solid surface like this. This is a solid surface. Clear? On this solid surface, let us say fluid is coming from this direction. Fluid is coming from this direction, and I am assuming that it is a continuum mass. Continuum mass means that the value of Knudsen number is less than 0.01. Continuum mass. The value of Knudsen number is less than 0.01. So now what will happen if the value of Knudsen number is less than 0.01? I told you that it will be a non-slip flow. Non-slip flow means that when the particles which are adjacent to the surface, what will happen is that, let me use another marker, what will happen is that they will stick to the surface. The particles will stick to the surface which are near to the surface. So if they stick to the surface, can I say that the velocity of this particle is 0? The velocity of these particles is 0? Yes, I can say that. Now what will happen if I am moving in the y direction? So this has particle velocity 0. But this fluid is coming from this direction. Okay, so what is happening is that as I am going in the y direction, vertical direction, slowly, if I observe every particle, and how to observe every particle, we have two approaches, Lagrangian approach and Euler's approach. What are those approaches? When I will be talking about the kinematics and dynamics, then we will be discussing that. Okay, but as we go in the vertical direction, slowly you can see that this particle has some velocity. Let us say it is u1. This particle has some velocity, that is u2. This particle has some other velocity, that is u3, and u1 is less than u2 is less than u3, and so on. And after some time, after the boundary layer, we have the stream velocity u infinite. That is, it was coming with u infinite. U infinite means at an infinite distance. It has a stream velocity. Clear? If I join, if at a particular point of time, I join all these coordinates, let us say at 2 seconds, at 3 seconds, at 4 seconds, if I join all these coordinates, what I will be getting is that I will be getting, this is the vertical direction y, I will be getting a profile like this. I will be getting a profile like this. I will be getting a profile like this, and that is known as the velocity profile. That is known as the velocity profile. So this particle has u is equals to 0, this has u1, this has u2, u3, and here we have u infinite. We have u infinite. So that is the velocity profile distribution. Now the question is, sir, why are you telling us this? Why not this viscosity? Why don't you come to the topic directly? Because this viscosity is directly related to this profile distribution, velocity profile distribution. Clear? Now how is it related? Now let me take two sections. One section. Let us say section. Let's say this section and this section. Let me take this section and let me analyze this section here. Clear? So this, let us say A, B, C and D. I have taken this section. This is A, B, here we have C and D. Like this. Clear? So this AB has velocity u2. This AB has velocity u2. This CD has velocity u1. Clear? This AB has velocity u2, this DC has velocity u1. Clear? Now we know that u1 is less than u2. It means that this velocity is smaller than this velocity. This velocity is smaller than this velocity, or I can also write u2 as u1 plus some change in velocity du. I can also write it like this. For example, it was 2 meter per second. It is, let us say, 2.5 meter per second. So can I write it as 2 plus du is 0.5? Can I write it like this? Yes, I can write it. So it is u1 plus du. So you can see that the upper layer is moving with a higher velocity as compared to the lower layer. So the upper layer is for example, both are moving, but upper layer is moving with a higher velocity. With a higher velocity, the upper layer is moving. So you can see that in between these two surfaces, or in between these two layers, we have a shear resistance. Again, let me explain you. For example, you have a friend of yours and who runs very fast, and if he runs 100 meter dash, then he comes first. And when you run 100 meter dash, let us say you come at 6th point or 7th point. Now I have tied you two people. I have tied the fastest runner and you are a slow runner. So I have tied you two people. I have tied the two people with a rope. And I have tied the two people. And I will say both of you just finish the 100 meter dash. So obviously your friend will be running faster than you, but you will be running slower. But what will be happening is that due to your slow running, your friend will also become slow after some time. So he will feel some resistance. And that property is known as viscosity. Resistance to flow. And why is it happening? Is it happening because of the shear stresses between the layers? So this layer is trying to pull this layer, but this layer is trying to restrict this layer. So if there is difference between the velocity, there are some shear stresses developed between two surfaces or two layers. So that is the reason the viscosity is being generated. That is the reason of viscosity. Clear? To understand this property, that is viscosity, we have a law. That is known as the Newton's law of viscosity. Clear? Newton's law of viscosity. What is Newton's law of viscosity? We'll be dealing with that also. But that is the concept of viscosity. Why viscosity is being generated. Clear? So whenever you have any solid body, it is going inside a liquid. Whenever you have any solid body, it is going inside a static liquid. It will always have some shear resistance. For example, let us say this is a duster, and I have a container, and that container is in a state of rest, and that container has water in it. If I put this duster inside that water and I try to move this duster, so I will feel some shear resistances on the surface. Clear? So I can say that if I have a fluid at rest, which is not bound by any surface, if I have fluid at rest, okay, and if any solid is moving inside the fluid, that particular solid will resist some shear stresses at the surface. So that also I can say. Clear? And that property is known as the viscosity. Clear? Now let us understand about the viscosity. And I will also tell you one more definition of fluids from this viscosity. Now, if we have solids, so for example, you have a solid like this, It is a solid, rigid solid. If you apply some force on this solid, if you apply some shear force, what is shear force? Which is parallel to the plane, So this is a plane which is parallel to the plane. If you apply some force which is perpendicular to this plane, this is known as normal force. Okay, so if you are applying some force which is parallel to the plane, what will be happening is that if this is a solid, there will be some deformation in the shape like this. There is some deformation. This angle is phi, this angle is also phi. But you know that from the basic, you can say basic idea of class 11th and 12th also, you know that there is a term known as the Hooke's law. So what is Hooke's law? So Hooke's law says that stress is directly proportional to strain in case of, you can say, normal stress is acting, but if shear stress is acting, the shear stress is directly proportional to shear strain. This phi, this angle phi is known as the shear strain. This angle phi is known as the shear strain. Shear strain. That is the definition of Hooke's law. That is the definition of Hooke's law. But when it comes to fluid, okay, when it comes to fluid, if you have some fluid here, if you apply some force on the fluid and you remove that force, the fluid will never come back to its original position. But if you remove this force in case of solids, the solids will again come back to their original position. For example, if you have rubber, you try to stretch rubber with some force, it will get stretched, but when you remove the force, the rubber will come back to its original position because it is a solid. It has some elasticity. But when you have some glass of water, if you are tilting the glass of water, what is happening on tilting? The normal force is getting converted into shear force. If you are tilting a glass of water, after some time, the liquid will start coming out. Okay. So we can also say that the Hooke's law, which is valid in solids, is not valid in liquids. The Hooke's law, which is valid in solids, is not valid in liquids. So on the walls, which kind of tip floor, no slip condition? Yeah, on the walls there is no slip condition. Yeah. Can we compare viscosity of a fluid with adhesion or cohesion? The viscosity of a fluid with adhesion or cohesion, you can compare it with cohesion. You can compare it with cohesion, not adhesion. You can compare it with cohesion. Okay. So shear resistance and shear force. Shear resistance and shear force. Yeah, shear resistance and shear force. There are shear stresses and shear forces. What is the difference? I will be coming to that also. Don't worry. Sir, I will repeat again. Yeah, this is the question which I wanted to see. Sir, repeat again, because I was thinking that I have taught you a lot of things. Okay. So let me repeat it again. Okay. Okay, now let's repeat it. Can I have some water? Okay, let me have some water, then we will continue. Don't worry. Okay, let me rub this. Okay, I guess that you have noted this. Let me rub this and again explain you this. Okay, can I rub this? Shall I rub this? Yes. Okay, I am rubbing this and I am again explaining you. Don't worry. Okay, I am again explaining. Okay, I am rubbing this and I am again explaining. Okay, now let me again explain you. For example, let me take a solid surface. And everything what we will be discussing in fluid mechanics, we will be considering that the Knudsen number is less than 0.01. It means that it is a no slip condition. No slip condition means that the particles which are, you can say, in contact with this surface, due to the force of adhesion and van der Waals forces, they get stick to the surface. Clear? So fluid particle is coming from this. Due to the force of adhesion and van der Waals forces, they get stick to the surface if the Knudsen number is less than 0.01. Clear? Now what is happening is that these particles have velocity is equals to 0 because they are stuck to the surface. But as I am going in the vertical direction, as I am going in the vertical direction, I will be finding that this particle has some velocity, this particle also has some velocity, this particle also has some velocity. If I consider a time frame, let us say 1 second or 2 seconds, I will see that after 1 second this has reached here, after 1 second this has reached here, after 1 second this has reached here. So if I join all these points, I will be getting a profile like this. That is known as the velocity profile. Okay, so this has velocity u1, this has velocity u2, this particle has velocity u3, this particle has velocity u4, and after some distance, this is u infinite, which is the stream velocity. U infinite is the stream velocity. Stream velocity. U infinite is the stream velocity. Clear? Now, to make you understand what is this viscosity, let me take one section. This section and this section, the section. So let me draw this section here. So this is like this. So these sections are 2 layers, you can say 2 layers are these, because this fluid is made up of infinite number of layers, infinite number of very thin layers. Okay, we can also imagine it like this. Okay, it is made up of infinite number of layers. So I am taking these 2 layers. Okay, this is A, B, C, D, A, B, C and D. So you can see that this AB layer has velocity u2, this DC layer has velocity u3, u2 and u3, and we know that u2 is less than u3. If this is 1 meter per second, this can be 1.5 to whatever, but it will be greater than that. So u3 is greater than u2. Clear? So now, if u3 is greater than u2, this u2 is offering some resistance on the layer DC. This layer AB, which has a velocity of u2, is offering some resistance on the layer DC. To make you understand how is it offering the resistance, I give you an example. Let us say that you are 2 friends, okay, one runs very fast and one runs slow, but if I tie those 2 friends with the help of a rope and I tell them to run, then the one friend will be running fast but one will be running slow, but due to this slow friend, your fast friend will also become slow after some point of time. It means that this slow friend is resisting making some resistance to the fast friend. It is trying to make the velocity of this friend also slow. It also wants that you also run with my speed. So it is offering some resistance to this velocity. And that resistance, that property, that resistance is known as the viscosity, That resistance to flow, because we are discussing fluids, so that resistance to flow is known as viscosity. Clear? Now, I also drew this. To make you understand, for example, this is some force is acting on a solid. This is a solid. Now, why I drew this? Because this is an interview question. The question was like this, because when I will be telling you about the Newton's law of viscosity, the question was like this: why Hooke's law is not valid for fluids? Why Hooke's law is not valid for fluids? First of all, you must know what is Hooke's law. So in class 11th or 10th also you must have studied that. Sigma, that the stress is directly proportional to strain. Stress is directly proportional to strain. And we know that stress is equals to modulus of elasticity into strain. And stress is given by sigma is equals to E into epsilon. Clear? That is the Hooke's law is valid in case of a normal stress. If you have shear stresses, so shear stresses are denoted by tau. This is denoted tau, T-A-U, tau. Clear? Shear stress is directly proportional to shear strain. This angle, this phi is known as the shear strain. Okay? So tau is directly proportional to shear strain. The question was like this: why Hooke's law is not valid for fluids? Why do we have a different law that is known as the Newton's law of viscosity? Why Hooke's law is not valid? So that is what I was trying to explain you. Why Hooke's law is not valid? Because, for example, if you have a solid body, if you apply some force and you remove that force, after some time the body will return back to its original position. And to make you understand, I gave you example of a rubber. If you stretch rubber and if you remove the forces, it will again come back to its original position. That is known as the properties of elasticity. Clear? But as far as the fluids are concerned, for example, if you have fluid like this, and it is inside walls, it is inside, you can say, walls, okay? Now you apply some force on these walls and you remove these walls. So what will happen? The fluid will keep on flowing like this. The fluid will keep on flowing like this. Even if you have removed this force, because the force of attraction between particles in a fluid are very less as compared to that of solid. That is why even if you apply a small force, it will keep on flowing. It will keep on flowing means that this phi, that is the shear strain, it will keep on changing with time. It will keep on changing with time. On 1 second, it is this. After 2 seconds, it will be like this. After 3 seconds, it will be like this. So this phi will keep on changing with respect to time. So that is why Hooke's law is not valid. Hooke's law is not valid in case of our fluids. And from here, we have another definition of fluids. We have another definition of fluids. The another definition of fluid is that fluid is a substance. If you apply a force on that substance, the shear strain keeps on increasing. The shear strain keeps on increasing. That is also a definition of fluid. That the shear strain, it keeps on increasing with respect to time. It keeps on increasing. That is also a definition of fluid. Clear? Now this is what I was trying to explain you. Now let us consider a section. Now let us consider a small section like this. Let us consider a small section like this. Okay? Now let us consider this section. This section I am considering this section. In this celestial I am considering this section. So this is the base, solid base, and I am considering this section. It is parabolic. It is parabolic. Clear? If this section is very small, this parabolic nature of the velocity profile can be considered to be a straight line. If this is very small, it can be considered to be a straight line. So let me consider it to be a straight line, not parabolic. For a very small region, let me consider it to be a straight line like this. Let me consider it to be a straight line. Clear? Okay, let me consider it to be a straight line. Now let us understand what is Newton's law of viscosity. Newton's law of viscosity. What is Newton's law of viscosity? Newton's law of viscosity says that the shear stresses, somebody was asking me, sir, what is the difference between shear stresses and force? So if you multiply the shear stresses with the area, you will get the force. Okay, so Newton's law of viscosity says that the shear stresses, what is the unit of stress? Newton per meter square, the same unit as pressure, Newton per meter square, Pascal. Clear? That the shear stresses are directly proportional to the rate of change of the shear strain, d theta divided by dt. d theta divided by dt. Never ever, this is the very common mistake, never ever tell anyone that tau is directly proportional to du by dy. Never tell anyone this. I will explain you how this has actually come. I will explain you, but whenever somebody is asking you what is the Newton's law of viscosity, always tell him or her that the shear stresses are directly proportional to the rate of change of shear strain. It can be theta or phi. So here for the Hooke's law I consider it to be phi. For this, let us say it is theta. For fluid it is theta. For fluid it is theta. Let us say this is theta. Clear? So what is the Newton's law of viscosity? The shear stresses in a fluid are directly proportional to the rate of change of the shear strain. The rate of change of shear strain. Now the question is, sir, but we know that tau is equals to mu into du upon dy. We know that. But sir, how it has been derived? If you are saying that tau is directly proportional to d theta by dt, it should be mu into d theta by dt. My answer is yes, it is mu into d theta by dt, but if I will be deriving something, then we will be seeing that d theta by dt is equals to du by dy. Don't worry. Clear? Now let me consider this element. Let me consider this element, this small element here. Let me consider this small element. So this is the solid surface. Let me consider this small element. So if this is a very small element, obviously I have drawn a very big element, but this is a very small element. So this change in angle, if it is coming with a velocity, the flow is coming with a velocity, this change in angle at some time, it will be very small. Let us say it is d theta. D theta. Clear? And this distance is also very small. I will consider it to be dy. Let us say it is dy. It is dy. Clear? If I consider time interval, let's say in 1 second, in 2 seconds, in 3 seconds. So if I consider time interval, this will be 0, u will be equal to 0. But if I consider time interval, let us say it is dt, very small time interval, let us say it is dt. And it is coming with a velocity, let us say this point has a velocity u. So how much distance it would have traveled in that time t? We know that distance is equals to speed into time. So u into dt, can I say? Can I say that du into dt? Because du is also very small change. Du into dt, can I say that? Yes, I can say that. Clear? Now from this triangle, now let me rub this. Now from that triangle, how much will be tan d theta? Tan d theta. So tan theta is equals to perpendicular upon base. So what is the perpendicular? Perpendicular is this. So this is du into dt. Du into dt divided by base. Base is what? Base is dy. Divided by dy. And we know that if this d theta is very small, then tan d theta is almost equal to d theta. Because tan 0 is 0, tan 0.15 is almost equal to 0.15. 0.0015, sorry, 0.0015. If it is very small. So tan d theta is almost equal to d theta. So can I write it like this? That du into dt upon dy is equals to d theta? Yes, I can write this. Can I write that du upon dy is equals to d theta upon dt? Can I write like this? Yes, I can write. Clear? So, and we know that from the Newton's law of viscosity, tau is directly proportional to d theta by dt. That is the original definition of Newton's law of viscosity. But we know that d theta by dt, that is the change in rate of the shear strain with time, it is actually equal to du by dy. So we will say that tau is directly proportional to du by dy. But if somebody is asking you what is Newton's law of viscosity, never ever say that the shear stress is directly proportional to the velocity gradient. Never ever say. That is a wrong definition of Newton's law of viscosity. Clear? So the correct definition of Newton's law of viscosity is that tau is directly proportional to rate of change of shear strain, is the Newton's law of viscosity. So obviously this is proportional. We will have some sign of proportionality also. So that sign of proportionality, tau, is actually denoted by mu into du by dy. And this mu is the coefficient of viscosity. Coefficient of viscosity. Somebody also get confused with the coefficient of viscosity. If I ask them what is viscosity, they say mu. Mu is viscosity. Mu is not viscosity. Viscosity is the resistance to flow. That is a property. Mu is not a property. Mu is a constant. Mu is a constant. Mu is not a property. Clear? So tau is equals to mu into du by dy. And du by dy is also known as the velocity gradient. Velocity gradient. Remember one thing, from now on, if somebody is saying you gradient will always be with respect to, generally it is with respect to distance. Generally it is with respect to distance. Pressure gradient, what is pressure gradient? dP by dy. What is shear gradient or the velocity gradient? It is du by dy. So it is generally with respect to distance, gradient. Gradient is generally with respect to distance. Sir, please explain once again. Don't worry, I will again explain you. Don't worry. Clear? So tau is equals to mu into du upon dy. Don't worry, I will explain you, don't worry. But let me first of all finish this. Regarding this mu. Clear? Mu is known as the coefficient of viscosity. Now let us understand about this mu, coefficient of viscosity. Now what does this coefficient of viscosity, it tells us? If the coefficient of viscosity is high, it means that that particular fluid will have higher resistance to flow. If the coefficient of viscosity is small, that particular fluid will have lower resistance to flow. That is what it is actually telling us about. Because if the coefficient of viscosity is high, the shear stresses will be high. If the shear stresses are high, it means that you can say one layer is going with a very high velocity and another is going with a very low velocity. You can also say that. Clear? Now let us understand about this mu, that is the coefficient of viscosity. Oh, sorry, I rubbed it. Shall I rub it? Okay. Shall I rub this? Okay, sir, is there a u1 minus u2 which is du? Yes, u1 minus u. Don't worry, I will be telling you that also. Du is a very small change. For example, I told you that this is u1, this is u2 and u3, and I told you that u3 is equals to u2 plus du. So this du is very small change. This is du, small change. Now let us understand about this term, that is the coefficient of viscosity mu. Mu, that is the coefficient of viscosity. Clear? First of all, what should be learned from this coefficient of viscosity? First is the dimensional formula of coefficient of viscosity. We know that tau is equals to mu into du upon dy. Clear? Now what is tau? So tau, we know that it is the shear force per unit area. Tau is the shear force per unit area. What is the unit of force? Newton. So it is Newton. What is the unit of area? Meter square. SI unit. I am talking about SI unit. It will be equal to mu, I don't know. What is this? U, meters per second. Meters per second divided by dy is meters. So meter get cancelled out. Clear? So mu will be equal to Newton second per meter square. Newton second per meter square. Clear? What is this Newton per meter square? What is this Newton per meter square? This is known as Pascal. So Newton per meter square is known as Pascal. Pascal. PA. So can I say that the SI unit of mu is Pascal second? So Pascal second is the SI unit of mu. Clear? Another important thing which was asked in 1992 gate examination, 1997 gate examination, also in a lot of gate examinations. Okay, so the dimensional formula for mu. So mu is equals to Newton per meter square. What is the dimensional formula for Newton force? That is MLT minus 2. If you remember, MLT minus 2. MLT T minus 2 multiplied by second, and for dimensional formula second is time T divided by meter square, that is length square. You know all these things na, M, L, T, what is M, what is L, you remember? Okay, let me tell you, okay. So now what is L? Stands for mass, L stands for length, and T stands for time. T stands for time. We also have theta also. Theta stands for temperature. But now we are in this, we are not using temperature. So theta also we have. Theta stands for temperature. So it is generally MLT minus 2. MLT minus 2 into T divided by L square. So if you solve it, you will be getting mu is equals to L get cancelled out. So it is T minus 1. So ML minus 1 T minus 1 is the dimensional formula for mu. Dimensional formula for mu, very important. Dimensional formula for mu. Clear? And how this MLT minus 2? We know that force is equals to mass into acceleration due to gravity. Mass has M, acceleration has meter per second square. So length second square. So it is MLT minus 2. Okay, so it is meter per second square, and mass has kg. Kg is M mass. So ml minus 1 T minus 1 or Pascal second. That is the SI unit. SI unit. Clear? Now let's go to the CGS unit. What is CGS? So CGS. Clear? So we have done about the SI units. Clear? So now let's go to the CGS unit. That is the centimeter, gram and second. Centimeter, gram and second. Okay. Now if go to the CGS units, instead of this Newton, we know that the Newton in CGS is termed as dyne. D-Y-N-E, dyne. So mu will be equal to dyne multiplied by second will be second, and length will be equal to centimeter divided by centimeter square. So this is the CGS unit of mu. That is the CGS unit of mu. That is the CGS unit of mu. Clear? That is the CGS unit of mu. And this unit in CGS is termed as poise. P-O-I-S-E. Poise is termed as poise. The CGS unit is also known as poise. Okay, so let me see the question. Don't worry, I will repeat that again. Don't worry, I will repeat that again. So please explain this triangular diagram. Okay, don't worry, I will explain the triangular diagram also. Yes, sir. Okay, sir. How it became du? Don't worry, I will telling you how it became du. Don't worry, I will be repeating that. Sir, please explain this triangular diagram. Okay, I will be explaining, sir. If the fluid flows without in contact with the surface, throwing it, any viscosity come into play or not? Okay, because then the no slip condition, we will not be with layers as expected. Okay, correct. Okay, I will be coming to that also. Don't worry. Okay, don't worry, I will be coming to that also. Clear? So this CGS unit is known as poise. Now the question is, which value of mu has to be remembered? Which value of mu has to be remembered? So the coefficient of viscosity of water is important. So the coefficient of viscosity for water is 1 centipoise. Centipoise. Cp. Cp means centipoise. What is centi? Centi is 10 raised to the power minus 2 poise. Okay, or you can say that 10 raised to the power minus 2 poise at 20 degrees Celsius. At 20 degrees Celsius. At 20 degrees Celsius. That has to be remembered. That has to be remembered, because I have seen that in GATE examinations questions are coming that fluid has a viscosity 100 times than or the 200 times than that of water. So what is the viscosity of that fluid? If you don't know the viscosity of water, you will not be able to get the answer. Clear? So this was all about viscosity. Now let me again repeat it, because somebody was asking, sir, what is this du? Somebody is saying that if there is no contact, then will the velocity will come into picture, viscosity will come into picture. Okay. So now let me come to this topic also again. Okay, shall I rub this and repeat it again? Shall I rub this? Okay, now let me rub this and repeat it again regarding the viscosity, okay? How we have derived the formula. Okay, now let me rub this. Okay, so from tomorrow I might be increasing my time, okay? I might be increasing my time, because if I am answering you a lot of questions, then fluid mechanics will be finished in 2 years, I guess. Right? Then from tomorrow I have to increase my time. So from tomorrow I guess it will be 3 hours. I will be asking them regarding 3 hours, okay? Otherwise fluid mechanics will be finished by 2021 August. Okay? 2021 August. Okay, so let me take this surface. Let me again take this surface. Fluid is coming from this direction with the velocity u infinite. U infinite, I can term it to be the velocity. If no slip condition is there, if the no slip condition is there, if the Knudsen number is less than 0.01, somebody is saying that, sir, if there is no slip condition, if there is slip condition, it means that the molecules are slipping at that time. At that time, it depends where are you providing the force. For example, if you are providing the force at this point, if you are providing some force at this point, if it has relative velocity, there will be shear stresses. But if all the layers are moving with the same velocity and there is no slip happening, there will not be any shear stresses. There will not be any shear stresses. Okay, it depends on whether the velocity is equal or not and where are you providing the force. Okay, if there is a slip condition, if slip condition is happening, then there will not be any shear stresses due to that particular layer, due to that particular, you can say, boundary. Clear? So now when it is coming, the Knudsen number is less than 0.01, so the particles will be stick to the surface. If I move upward, so we have a velocity profile distribution like this. Clear? Now, here the velocity of particle is 0, it has some velocity u1, it has some velocity u2, and so on. So I can say that at every point, at every particle has some different velocity. So what I am doing is that I am taking any section. I can either take this section or I can take this section or any section, any small section. I am taking any small section. So let me take one this. If you are confused with why I have taken this, why not this, let me take that also. I can take this section also. If I am taking this section, then here this upper one has a velocity of u1 plus du. The lower one has a velocity of u1. Clear? If I multiply it with the time, if I multiply it with some dt, this particle would have traveled only this much of distance, this particle would have traveled this much of distance. If I draw perpendicular, again I will be getting the same diagram. Okay, and this distance will be equal to du into dt. This distance will be equal to, this is d theta, and this distance will be equal to du into dt. For how much length? For a very small section, that is dy. And now don't get confused, because in the earlier derivation I took this section. I can take any section, because somebody was asking me, sir, why this, from where this du has come. So to make you understand where this du has come, I have taken this section. I can take this section also. Clear? So tan d theta, same thing. So tan d theta is equals to d theta is equals to du into dt divided by dy. and d theta divided by dt will be equal to du into dui, and same thing which we have got, So from here we have got the value of du. Okay, sir, thanks. Okay, doubts. So pump part. Okay, I know that pump part seems to be a very difficult part, but don't worry, we'll be going to the pump part with this speed only. Okay, don't worry about that. Okay, so dekho, you asked me so lot of questions. So what happened is that the time is over. So from tomorrow, what I'll be doing is that I'll be taking 3 hours. Okay, because 2 hours is very less. Okay, so from tomorrow I'll be taking 3 hours, because otherwise it will take a lot of time. Because as soon as we finish our syllabus, because my only motive is that you practice a lot of questions. So students who have already heard me a lot of times, I always tell them we should practice a lot of questions. Okay, for example, when I was preparing for GATE examination, when I had some weak concepts in some subject, so what I used to do is that I used to keep the book aside, I used to solve some questions, and by solving some questions I used to get the concept. Okay, this is the concept. Okay, so if you are facing any difficulty in the concepts, I would recommend that go and solve maximum number of problems. It can either be numerical problem, it can either be theoretical problem, whatever you have. Okay, so from tomorrow I will be taking some more time, because today I wanted to solve some questions, but due to lack of time we could not. Okay, sir, please increase the pace as a lot of syllabus. Yeah, that is why I am saying. From tomorrow I will be taking 3 hours class. Okay. Because I don't want that because obviously some students must be having some concepts of fluid mechanics, and they want that me to finish the syllabus as soon as possible. But we also have to take into consideration those students also whose fluid mechanics is at 0 level. Because when I started preparing for GATE examination, my weakest subject was this fluid mechanics. When I started preparing for GATE examination, so obviously I had to put a lot of efforts in fluid mechanics, and today you can see that I am teaching you fluid mechanics. Clear? So that is the thing. So we have to take into consideration that student also who has very weak concepts in fluid mechanics. I am of 0. Yeah, even I was 0. So relation between Newton second per meter square and poise, both are the same thing. Newton second per meter square, poise, both are the same thing. Clear? Okay, so that is mu is equals to Newton second per meter square, that is known as poise. Okay, and Newton per meter square is known as Pascal. So we can also say that the SI unit of this is Pascal second. Okay, and when we went to the CGS, that is dyne second per centimeter square, and that is poise. And if you look at this, so dyne is what? So dyne is, if you remember, so one dyne is 10 raised to the power minus 5 Newton. One dyne is 10 raised to the power minus 5 Newton, and 100 centimeter is equals to 1 meter. 100 centimeters is equals to 1 meter. So if you put all these values here, so what you will be getting is that 1 Pascal second is equals to 10 poise. 1 Pascal second is equals to 10 poise. So you will be getting this relation. Okay, don't worry, we will be continuing this from tomorrow also, that the relation between the Pascal second and poise, but both are the units of viscosity. Okay, so let's call it a day, because it's already 3:30. Okay, so let's call it a day. Okay, even I was 0. Yes, 1 Pascal second is 10 poise. Tomorrow we will be continuing this. Okay, so tomorrow we will be continuing this. Okay, so let's call it a day. Okay, thank you.